Headphones, etc., etc. Get all that stuff away. And let's focus on this. Learn it, and then you go practice it. All right, so absolute value. Tell me what you know about absolute value functions. I heard something. What do they do? Absolute value functions. How do I write it? I want to write the absolute value function. Okay, so I need absolute value bars. So I could write that, and that's going to be our most basic parent function, the easiest one we can write, and we'll talk about how to transform that. It's going to be easy for you because you've already had a lot of practice with it. But that's really the main thing we're going to talk about today. But what does this do? What does an absolute value function do? Yes, ma'am. Okay, it's always positive. So if I put in a positive answer, what's it do? It doesn't do a thing, right? If I put in a positive answer, it just stays the same. If I put a positive number, it doesn't do anything to it. But if I put in a negative number, what's it do? Okay, how do you change a negative number to positive? What do you do? Multiply by negative 1. Exactly. Yeah, and that always gives us the opposite, right? Okay, so there's one way we could write this then, an absolute value function, is we could say something like this. We could write it as what's called a piecewise function. Okay, you've probably heard that term and seen these before, but it may have been a while. So a piecewise function, you told me that it doesn't do anything if x is positive, or even 0 in this case, right? What's the absolute value of 0? 0. Okay, so if it's, how do I say numbers that are 0 or positive? Any idea? Yeah, that's true, but I actually give them a name. We'd say they're positive if they're greater than 0, they're negative if they're less than 0. What was it? Oh, I thought you said it, but maybe not. How would we say numbers that are 0 or positive? If they're 0 or positive, what are they not? They're not negative. But actually what we'd say is non-negative. Non-negative numbers would be 0 or all the positive. So if x is non-negative, it stays the same. That's what you told me, right? But if x is negative, we have to multiply by negative 1 to take its opposite. Okay, so that's how we write this as a piecewise function. There is another way to think about this that's kind of interesting. And it actually, I want to show it, it's not in the book, but I want to show it to you. Later on in the class, this will become a bigger deal. We could write it as, we could also write it like this. Why do you think that works? Because it does. Yeah, and if I square a number, a real number, what always happens? Multiplied by itself. If I square a positive number, it's like 3 squared is, what's negative 4 quantity squared? Okay, so if I square a negative or a positive, I always get what? I always get a positive. And so then if I just take a square root of that again, I'm always going to get back a positive answer, right? For example, if I were to do something like negative 4 squared is 16, square root of 16 is 4, right? So this actually does what we ask it to do, right? Okay, I'm going to hold off on this one just a little bit. We'll do that. That'll fit better maybe tomorrow. Let's just focus on this though. If I want to graph an absolute value function, we've written it as these two different pieces. They have these two different behaviors based on the value of x. Okay, so with a piecewise function, all we have to do when we're graphing a piecewise function is just graph all of the pieces on their domains. So if I want to graph the function y equals x, what does that look like, by the way? It's going to be a diagonal line, isn't it? How do we know, what are our cues that that's a line? The x isn't being squared, is it? The x is to the first power. And so that's telling us that If I have something like that where y equals x and it's not to any power, we know that's a line, don't we? Okay, and so then when we know it's a line, we're just going to try to fit it to the slope-intercept form and try to determine, what are the slope and y-intercept. So if we match that up to mx plus b, well, what's the coefficient of x here? 1. So slope of 1 is just rise over run is 1. So it's just a 45, right? 45 degrees. And b is, what am I adding to x? 0. So it's going through the origin. It's got a slope of 1. Doesn't it just look like that? But notice the line y equals x continues on forever, right? But I'm only going to graph it on its domain, though, right? So I'm only graphing it where x is greater than or equal to 0. Does that make sense? Okay, in a piecewise function. So this is the function, but I'm only graphing it there, right? What does this one look like? That's a line too, isn't it? Greg, what's that going to look like? Y equals negative x. What's going to be my slope? Until negative 1. Yeah, what's my y-intercept? 0. So same thing, it's going to be, right, it's going to be here, isn't it? Right, that's the y-intercept. If I were to graph the line, I would probably rise by negative 1 and run by 1 to get a point there and just continue on. But we don't graph it there, do we? Right? We're only graphing it for values of x less than 0, right? So technically, I would have to put an open circle there, and I'm just going to extend the graph back that way. Does that make sense? Once again, this line goes forever, but we'll only get to graph it on that domain. Everything else gets erased. So then, how would you describe that? What's an absolute value function look like? What do you think? It's got that is the characteristic look. It kind of looks like a V, doesn't it? Yeah. Right? So it's got a sharp, point on the bottom. We call that point the vertex, because that's the only point on the curve that's really recognizable, right? But that's it. That's what it looks like. So then now the question is, how can we take this parent function and transform it? Well, you guys are pros at that. We've done a lot of that stuff. That's not a big deal. Before we launch into that any further, though, I want to kind of go back and maybe simplify a little bit of the stuff that we already learned. We can do something with this we can make it easier. Okay, and we're going to do this for the rest of the year. We're going to try to do things in the simplest, effective way, and that's the best way to do math. A lot of math, especially when you get into higher level math, and this seems kind of strange, but like in calculus, for example, I bet you, 80 to 90% of what I teach in calculus is not how to do the calculus, but how to do it the most simply, right? There's a lot of ways to do calculus problems, but to do it well, you want to do it in the most effective, simple way. And it's the same thing really with algebra too. So if we want to look at something like, let's take a parabola. Let's take the parent function f of x equals x squared. I want to show you something. I kind of briefly touched on this before, but I want to maybe explain it in a little more detail. If we want to transform this thing using all the parameters that the book talks about, we had 4 of them. Whenever we can, we always want to reduce that number to the smallest number possible. Well, one thing, it's a good book, but one thing that I'm not so crazy about is that they introduced this b. And I've told you before that the b is kind of not always necessary. And whenever we can, we want to eliminate it. Because wouldn't you agree, going back and thinking about all those problems we did, what was the hardest of all the parameters to deal with in terms of transformations? It was b, for sure, right? B is the one where you're more likely to make mistakes. So let's just get rid of it when we can. So instead of having to do this, is there a way we can get rid of that? Oftentimes there is. Most of the functions we deal with this year, we cannot have to mess with the b. Let's look at a parabola, for example. So if we take the parent function x squared and we write it in this way, wouldn't it just look like, I'm going to have an a out front, right? And then my function is what's the rule here? Whatever I'm putting into the function, I'm just squaring, right? So then, if f of x is x squared, what's f of 2? How'd you get that? So f of 2 is just 2 squared, right? What's f of a billion? Billion squared. What's f of a? A squared. What's f of the quantity a plus b? A plus b squared. And that's really important that you see that. Seems like a really simple concept, but if you get that kind of wired in your brain, that's really helpful in math, right? You're just following a pattern. So what's f of all this junk? All that junk squared, right? Everybody agree? So I could write this then as all that stuff squared, right? Everybody agree? And then just plus k at the end. Okay, well, why did I do that? Because there's something tricky we can do here. There's a property of exponents that, once again, you've probably talked about it, but it's probably been a while. What do you think I can do if I have something like the product of a times b to some power? Let's just call it the m power. Can I rewrite that in any way? Let's take numbers for an example. A lot of times it's helpful to just think of the example in terms of numbers. What if I've got 2 times 3 squared? So yeah, I could write it as 2 times 3 is 6 squared, which is 36, right, if I just follow order of operations. But alternately, what else could I do? You saw it, Trevor, what did you say? Okay, and you got the 4 because you said I could write this as 2 squared times 3 squared, right? So I could distribute that exponent to each of the factors, right? And I end up getting 4 times 9 equals 36. So in general, if I have something like a times b to the m, I could write that as a to the m times b to the m, if I want to, if it's useful, right? Well, it's useful here. How many things are being multiplied inside the brackets? Dante, how many things are being multiplied inside the brackets here?
What was that?
How many things are being multiplied inside the square brackets? 2. Good. I've got that thing, right? Good. I've got, that's one thing, and that's one thing, right? Because it's in parentheses, so it's a quantity, so we just treat it as one thing, right? So if I'm going to square that product, we could use that same property, couldn't we? We could take this exponent 2 and just distribute it to both of those things separately. Everybody see that? Okay, so then we end up getting, what's that give us? So we're going to get a times 1 over b squared, right, times x minus h squared plus k. Well, what is, here we got to use the property again, but it works for division also. So if I do a times b to the m, you know, we get a to the m times b to the m. What do you suppose happens if I do something like a over b to the m? What do you think I can do? Say, what do you think? Mark,
Just
what do you think?
divided by m squared.
So a to the m over b to the m? Yeah, it works. Okay. So then 1 over b squared is the same as 1 squared, which is over b squared, which is just b squared, right? So all this stuff out here, I could just write as a over b squared, right? Times x minus h plus k. Well, h stays the same. That's horizontal translation. K is vertical translation. But if all this stuff out front can be written as just one number, why even mess with calling it a and b? Just take that one number and have it be the original a, right? Because isn't a just whatever number we're multiplying by the function? You see what I'm saying? Okay? So that tells us something interesting. That tells us, and this is, I don't, this is where just really try to get this concept, because this is why I think math can be so fascinating. if you can take that simple algebraic concept and think about it in terms of what it actually does, that tells us that if I don't have to have an A and a B, right? Because let's put numbers in this for a second. Seriously, don't just, you gotta, every once in a while you gotta embrace your inner geek a little bit and just kind of let this stuff be interesting, right? So let's take an example. What if I have something like g of x equals 2 times 2 times 1 over, let me make that a 4. Actually, I'm going to make that 8. Yeah, okay, so what's the value of A in that? 8. What's the value of B?
2.
2, okay. H is -2, and K is 3, right? So technically, if we want to think about that in terms of the 4 transformations, that's a vertical stretch by 8, a horizontal stretch by 2, right? Sliding it left by, or right by 2, right? Because H is positive 2. And then going up by 3, because K is 3. Agree? But that's 4 things. That's sort of complicated. Let's do our little trick, and let's distribute this squared, which is supposed to be out there, sorry. It's supposed to be out there. We're going to distribute that to both parts, right? So now it ends up looking like 8 times 1 over 2 squared times x minus 2 squared plus 3. But what's that going to be? What's 1 over 2 quantity squared? 1 squared over 2 squared, right? So what is that? 1/4. So this just becomes 8 times 1/4, which is what? 2. Aha. So we can write that thing out front as a 2, and then all the other stuff we didn't change, right? So that just becomes x minus 2 squared plus 3. We just did something really amazing, because what does that look like now? That looks like horizontal translation to the right of 2, up 3, but the number out front is what? A or B? A, and it's 2. So we could do 1 vertical stretch by 2 is equivalent to doing a vertical stretch of 8 and a horizontal stretch of 2. Isn't it easier just to do 1 simple vertical stretch? Right? You see the whole point of this? So what that tells us is that if we don't need to have both horizontal and vertical stretches, it tells us that for that shape, for a parabola, stretching it vertically is exactly the same thing as compressing it horizontally. Doesn't make any difference, right? The shape goes on forever, and if I smash it horizontally, that's identical to what it would look like if I did that to it. If I squash it vertically, it's going to look identical to as if I had stretched it out horizontally. So why do both? Just do the easiest one, which is the vertical one, right? So from now on, we never ever, and if the book does, I just won't ever use those problems because, there's no need. We can always just write a parabola like this. There's no reason to make it more complicated. The B doesn't add anything to it. Okay? See what I'm getting at? Questions on that? Okay. Well, let's go back now. So we got off track. Let's go back to our absolute value function, right? We said that we have this parent function, f of x equals absolute value of x. Now let's think about this in terms of all 4 of those parameters, and you tell me if you think we need them all, okay? And even if we look at the shape of this, if we look at the shape of this function, it's just a v, right? What do you think? If I stretch that vertically, what's it going to do to the v? Yeah, it's going to make it kind of taller and skinnier, right? If I compress it horizontally, is it going to look any different? It's going to be the same, isn't it? Everybody agree? Because these are just straight lines, right? They go forever. If I compress it vertically, that's got to be the same thing as stretching it horizontally, because it's not changing the shape of those. They're lines, right? So what do you think? Are we going to need both the A and the B then?
No.
We shouldn't, right? We shouldn't need them both. So think about this now in terms of both the a and the b. So we get the absolute value of 1 over b times x minus h plus k. What do you think I could do, Molly, what do you think I could do if I have the absolute value of a times b? Do you think I could rewrite that? Could I separate those? I can't, can I? Because all this is doing is just making this product positive, right? It doesn't really matter if I'm gonna, let's take numbers for example. If I take the absolute value of -2 times +3, I just get 6, don't I? Right? If I split this apart into the absolute value of -2 times the absolute value of 3, I'm still going to get 6, right? It doesn't matter when I make this positive. I could make the individual factors positive at the beginning and then multiply, or I could multiply first and then make the whole thing positive. Doesn't make any difference, does it? So I can always just split this apart like I did with the x squared. Agreed? So then up here in my function, look what I can do. If I'm taking the absolute value, Dante, how many things am I taking the absolute value of? 2. Oh, gosh. I've got this thing, and I've got that thing, right? So I could just split them into separate absolute values and get a times the absolute value of 1 over b times the absolute value of x minus h plus k. But isn't that just going to be a number? Right? It's just going to be some number. So call it a. We don't even need the b, do we? Right? So we don't have to. So when you when you do the reading in the textbook and it talks about the b, just kind of know that we don't need it, right? We can instead always write an absolute value function like this. And we know what a, h, and k are. Those are the easy ones, right? Okay, so then what if I want to do something? So the first assignment is really just stuff like this. What if I want to graph the function g of x equals 4 times the absolute value of x minus 3 plus 2? How am I going to do that? I'm going to start with my parent function, which is just that v, right? And how am I going to tweak it? So here's my parent function, right? What are the parameters there? What does this 4 represent? Which parameter is that? I mean, which one is that? It's what's being multiplied by the fraction. So that's a, isn't it, right? So we know that a equals 4. What's that do? Stretches vertically. Okay, Richard, what's this one right here? One that's being subtracted from x inside the function. H, good. So h equals 3, right? That's what's being subtracted from x. What does h equals 3 do? No, if h is positive, I'm moving to the right. That's the one that's a little bit tricky, right? You're going to translate horizontally opposite whatever that is, right? So we're going to the right by 3 because I'm subtracting 3. And then last one, Bailey, what's this one right here at the end? The one I'm adding out at the end? K. K, good. So k equals 2, so that means I'm doing what? Up 2, right? So let's take this vertex then, and we're just going to translate this thing, where? Right 3, up 2. Everybody agree? So the new vertex is going to be right there. And what's the 4 do out front? If I stretch it vertically, normally I would go over 1 and up 1. So now when I go over 1, how far should I go up? 4. 4 times as far, right? So we'll go over 1 and up 1, 2, 3, 4. And then I can just reflect that thing over this line if I want to, right? That make sense? That's it. Okay, what if a had been, what if this had been -4? What does that mean if I multiply the whole function by -1? Yeah, that means I'm just replacing, because this is my y, right? So that means I'm reflecting it over the y-axis. Everybody agree? Okay. Buy that? Okay. Last thing. I'll let you guys work on this stuff. So when we look at this graph, does it have symmetry? It does. We kind of even just talked about it. I sort of gave it away in the last example. It has folding symmetry over what line? The y-axis, right? What did we call that? What kind of symmetry did we look at? You remember? We had two kinds of symmetry. If we fold it over the y-axis, is that even or odd? It was even. Odd was the spinning symmetry, right? The rotational symmetry. So this is even symmetry. Even symmetry was the one where if I go over positive x or back negative x, the y value should be the same, right? Either way. Okay, if I go over x and I go up to this is my function f, if I go up that far, then that must be a y value of f of x. If I go back to negative x, the y value has to be the same thing. It's going to have that kind of symmetry, right? That works, doesn't it? For an absolute value function. What if I put in a negative x? What's the absolute value of negative x? Positive x, right? It's the same thing I got when I put in a positive x, right? So it's got that even symmetry. Yes, sir? Yeah, you bet. Okay, make sense? I think you're good. I think you can do this stuff. Let's go. How much time we got? Oh, we got a little time. Let's go down to 205.
Thanks, Steph.